Today, I would like to introduce our speaker. Okay, first, my name is Raphael, and today I would like to introduce our speaker, Sai, who is a machine learning engineer at Pinterest. So a little about our speaker. Sai is a machine learning engineer from Pinterest. She works on building shopping recommendation systems and improving the mid-funnel shopping experience on shopping surfaces at Pinterest. Before Sai joined Pinterest in 2018, she also worked as a data scientist in a few companies such as Liberty Mutual, eBay, and Apple. She received a PhD in statistics from UC Santa Cruz. So our talk today is titled Shopping Recommendations at Pinterest. The abstract: millions of people across the world come to Pinterest to find new ideas every day. Shopping is at the core of Pinterest's mission to help people create a life they love. This talk will introduce how Pinterest shopping team builds related product recommendation systems, including engagement-based and embedding-based candidate generations, indexing, and serving methods to support different types of recommenders and their deep neural network ranking models. That's a mouthful. But without further ado, please, I leave the floor to Sai. Sai, please take it from here.
All right, thank you for introduction. I'm Sai Xiao from Pinterest. I'm currently working in shopping discovery team based in Palo Alto, California. I have joined Pinterest for 3 years, so today I'm very excited to introduce you shopping recommendations in Pinterest. Cool. So Pinterest is the visual discovery engine, and our mission is to bring everyone the inspiration to create a life we love. On Pinterest, people share billions of pictures and explore for new ideas, such as travel, cooking, home improvement, fashion, and beauty. So we use the term pin to refer to those images, videos, or stories shown in Pinterest. And the pinners collect the pins and organize them into boards. So there are many ways to play with Pinterest app. For example, when you open the Pinterest app, and before you do anything, you can see we already prepare pins that you may be interested in. Those pins are generated by our recommendation systems based on your interest and behaviors. And when you browse them and take actions on them, we will get more information about your interest and then iterate your homepage. Besides, you can also do keyword search or visual search, and we will retrieve and recommend relevant pins to satisfy your query. And when you click into a pin, we will also show you some similar ideas. So we are actually really good at recommending organic pins in these services. And now we are taking what we learned in these services to develop shopping recommendations. More than 450 million people from around the world come to Pinterest each month. And we have 300 billion of pins saved in Pinterest and 6 billion boards created. From the boards and pins user collected, we find a lot of shopping intent in Pinterest. Shopping has a great potential in Pinterest. And according to a public survey, 83% of the pinners have made a purchase based on the content they saw from boards on Pinterest. Shopping is also growing fast in Pinterest. We observe more shopping browsing. So there is 215% growth in the number of pinners engaging with shopping services on Pinterest in the past year. There is also much more discovery about around shopping. So product searches grow by 20 times in the last year. And the shopping is also now global. We are live in US, UK, and Australia, Canada, France, and Germany. So it's officially global. We provide different entry points for the pinners to get to the shopping services. And here I want to give you a few examples. So the close-up shop. So when users tap into a non-product pin, the object detector will identify the products in the home decor and the fashion categories. And once you tap into the tag, and you will find product recommendations. They look very similarly to the object that you tapped. And for very high shopping intent search queries, we also offer Shop Tab feature. We show product pins from different merchants available in your geographical locations. So those products are organized by different recommendations. For example, shop by brand, shop by categories, or shop by styles. And we try to show accurate and complete product metadata for products. And we also cover tens of thousands of merchants. And under the product details, we offer multiple recommendations. So the related product recommenders provide the most relevant pins, such as substitutions and visually similar pins. And we also leverage those recommenders, such as more products from the same merchants, or recommends the most popular products from the same category. And besides that, we also build recommenders based on collaborative filter to learn from the co-occurrence of two products to recommend people view, also view, or people view, also board, or some products they bought together. So the remaining of this talk, we will focus on introducing the tech stack of building these shopping recommendations on product details page. First, I want to look at some challenges of building a recommender system. First is the massive scale. And we have hundreds of millions of product pins in the catalog, and we need to serve the recommenders for hundreds of billions of pinners. Second, in today's recommender system, the feature data types become much richer. It has user-level features, text, image, video, and graph. The recommenders also need to optimize multiple objectives, such as different types of engagement or relevance. And also we need to balance the fairness and the diversity of the merchant and inclusiveness, such as skin tone. Next, not a single similar recommenders will fit shoppers' intent. We need to build multiple recommenders to accommodate different shopping intent. So one problem is how to develop a new recommender fast. Last one but not least, once we have multiple recommendations, we need to optimize the whole page to decide which one and where to display in which UI. So this is the system overview of our current system. So first, we have to build a huge product catalog, which includes both the merchant ingested product pins and the user provided pins to power all the shopping user cases on Pinterest. So this is the backbone for all the shopping features. And the recommenders consume the product catalog to retrieve and provide different types of recommendations. On top of all the recommenders, we have shopping page optimization mechanism to select a decent number of recommenders to show to the users and decide which recommender to rank the top. This will significantly improve the user shopping experiences and also reduce the cost of showing too many recommendations for the users. The whole stack supports multiple shopping surfaces, such as product detail page, shop tab, and shop tab in search and shop tab on board. So next, I will focus on to introduce some details of building product recommendations. And we mainly focus on introducing the product recommendations in the context of product-to-product recommendations. The system actually will take in the product query, a query product, and the user information as the input. And we output a set of products that are similar to the query product and match the user's preferences. The whole recommendations can break into candidate generator phase and the ranking phase. The candidate generator phase will take in the query and sometimes the user as an input. It retrieves sufficient but most similar candidates from the catalog, which is around 100 million product pins. And then we rank those pins by machine learning algorithm to rank the candidates and select the top K results. We also apply a relevance guardrail such as gender match and broad category match and the trust and safety check to trim some irrelevant pins before serving to the users. Okay, so let's talk about candidate generator. We built the candidate generator through several sources, such as MapBoost by utilizing the historical engagement, the candidates based on pinboard graph. And one of them works particularly well is embedding-based candidate generator, which leverages the deep learning models. There are two basic problems associated with embedding-based candidate generator. One is how to generate embedding representation for the pins. We have DNN model to generate product embeddings for the whole catalog and save them into embedding store via offline workflow. The other problem is how to retrieve the retrieval model. In the online serving phase, we look up the embedding for the incoming query from the embedding store, and then do a nearest neighbor lookup from the whole embedding store to select the top K candidate pins. So let's see first how we built our unique embedding for billions of pins and millions of product pins in a scalable way. So Pinterest has a lot of graph data. As I just introduced that, user can collect the pins into their board. So it's basically will construct a bi-party graph. How do we use graph as our input feature? Here at Pinterest, we have a very unique way to create product embeddings. We utilize two things. One is the pin board graph. People use Pinterest to save boards, organize them, and which are actually visual bookmarks to online content, like recipes, clothes, products, onto the boards. And we model the Pinterest environment as a bi-party graph consisting of nodes in these two disjoint sets, pins and boards. And then we use the graphical model. The benefit of this approach is that by borrowing the information from nearby nodes, the resulting embedding of a node become more accurate and more robust. So think about a bed rail pin, just a pin, might look like a garden fence, but gates and the beds are rarely adjacent in a graph. So our model relies on this graph information to provide the context and allowed us to disambiguate pins that are visually similar but semantically different. So each pin is associated with multiple data types, providing certain information like image and a set of contextual annotations like titles and descriptions. So we can incorporate these visual embedding features and also text features to combine the characteristic from both image and text. And the graph feature is by utilizing the pinboard graph and localize the convolution operation. We apply some aggregation algorithm and provides a vector representation of its local neighborhood. And then we concatenate the aggregated neighborhood vector and the node's existing representation and transform the concatenated vector through another dense neural network layer. We have millions of users engaged in the Pinterest pins, so we have a huge amount of engagement data like clicks, save, and long clicks. So this model is learned from this historical engagement data and learned from the standard triplet loss. So one of the challenge is that we need to efficiently training our graph convolutional neural network model. So I think the most challenge key is that we need to scale both the training as well as the inference of the graphical convolution neural network-based node embeddings to the graph with billions of nodes. So, and over time, the pinboard graph is also growing and changing over time. So the PinSage leverages several key insights to dramatically improve the scalability of this graph model. So traditional graphical model recommender system require operating on the full graph during the training. And this assumption is infeasible when the underlying graph has billions of nodes and its structure is also constantly evolving. So our PinSage algorithm performs efficient and localized the convolution by sampling the neighborhood around the node and also dynamically constructing a computation graph. Secondly, how we select a set of neighbors to convolve over is also very important. In PinSage, we define importance-based neighborhood by simulating random walks and selecting the neighbors with the highest visit counts. There's more details from this KDD paper, so feel free to deep dive into that. So after we talk about how the embeddings is trained and generated, we talk about the serving part. We built the efficient approximate nearest neighbor search by leveraging our backend search engine as distributed serving platform for the KAN. And we retrieve the candidates by using the state-of-art KAN method, currently is HNSW algorithm. And we built this AN batch indexing, view Hadoop, and also near real-time indexing for fresh pins. For the candidate generator, we not only index PinSage embedding in the KAN search index, we also include other candidates into this search index. So we have a unified search index. So one of the requirements is that we need to search candidates by some constraints. One of the important component in our index framework is attributes. So the attributes are properties of each search document. Each document in the product corpus will have pin stage embedding associated with it, and other properties such as price, merchant, category, style, and etc. So at a high level, the framework manages the conversions of a corpus into a manus document, and then merge those search documents with some attributes used for filtering as the query time. So the benefit is that the shopping candidate generator can share a common set of product attributes, including fields required for internationalization. So this allowed us to define the attribute once for all the candidate generator and simplify the query composition as the serving time. This will increase the engineering velocity when we build other candidates generator and adding more constraints. Besides embedding-based candidates, we also have engagement-based candidates. So this collecting the historical user engagement data in the past year. So each query pin, we have a list of historical engaged pins as candidate source. So in order to index those map boosts into the same index, we converted the candidate pins to a list of query pins. So each search document actually has a list of query pins as the attributes. So with this flexible indexing framework, it helps us to onboard some of our new recommenders in a fast way. By configuring different attributes in the query composer, given that in the product corpus has contained all the required metadata. So if we specify the merchant restricts in the query, the retrieved candidates will own the candidates from this merchant. So we can build the recommender so-called more from this merchant. Or if you specify some category or style in the query, the retrieved candidates will only be the candidates with this category restrict. Okay, let's talk about ranking part. The primary goal of the ranker is to optimize the engagement, giving a query pin and the user information. And in Pinterest, we have different types of engagement. For example, save, that means you save the pin into this board. Or close up, that means you click one pin and look into the details. And the long clicks means you click the pin and outbound to the website and take some time in the website. And conversion, that means you check out some of the, you purchase some of the product in the website after browsing the pins in Pinterest. So there is a different types of actions, and we need to personalize our ranker. And of course, we have a large scale of historical engagement data for us to train this model. But how to deal with different types of engagement? We use a multi-head DNN model. We use different features, including pin stage embedding, user embedding, text match, and shopping signals. And then we use AutoML to construct a DNN by grouping all these features and the cross features in the fully connected layers. So Pinterest AutoML is a self-contained deep learning framework that powers feature injection and feature transformation, model training, and the serving. And the output of this model will have 4 output heads, which each corresponding to our engagement type. And the 4 output heads will borrow information from each other by sharing the previous layers. And this would also alleviate the overfitting problem. After that, we apply some numerical calibration method because we do downsampling the negatives in the training data. So after the calibration, the scores can be more accurate to interpret the probability of this type of engagement. In the last step, we combine all predictive scores by the utility function to generate a single engagement score to rank the candidates. So one probability score for each engagement type gives us great flexibility in ranking the candidates. So starting very simple, we consider just use a linear combination of the scores as the utility function. And one motivation is to decouple the business value from the engagement prediction. So we can adjust the weight in the utility function to accommodate some business engagement to emphasize on some type of engagement without retraining the predictive model. To summarize, we use the state-of-art recommend text to build our recommender system, both the embedding-based candidates and the multi-head DNN ranker, to help us to move the engagement metrics significantly. And ultimately, we want to build a unique shopping experience at Pinterest to help people get inspiration and ideas. Oh, sorry. Okay, yeah, I think this is my talk. Thank you very much for listening to my talk. And yeah, feel free to ask questions.
Awesome. Thank you so much, Sai, for that really interesting presentation. We do have a couple of questions on here, and I'll just read them out to you. So Ganeshan asks, how are the 20 billion edges stored and retrieved during training?
During the training, I see. So actually it's a very good question. So here, I think this is an offline workflow that we do have some workflow to extract to extract the local neighborhood from the offline workflow.
Got it.
Yeah. So it's not the whole not the whole graph.
Makes sense. And then there's another question here from Rui Hua. How do you assess the quality and performance of the generated graph-based GCN embeddings or graph stage embeddings?
Yeah, that's also a good question. So usually we have a golden data set to have, for example, if we have the query pin and the candidate pin, so we already have a golden data set to know that the ground truth. And then we usually measure the recall, like in top 10, to measure the performance of the embedding.
Got it. So there's a couple of more questions coming from Rui Hua also, and I'll just read them both out to you. So are rare items post challenge? Are rare items post a challenge for GCN or for the embedding space itself? And then the other question also from the same person is, given the number of items for embedding, how many data are needed to do a good embedding? I don't really know what that question means, but okay, maybe you understand.
Given the numbers of items.
For an embedding, maybe it's asking, or maybe the question is
like the data size of the training data size?
Yeah, exactly. Is there a limit to, I mean, obviously there's always a lower bound limit. I don't think there's a upper bound limit, but yeah, can you speak to that?
Yeah, I actually don't know quite the exact number of the data size of the training data set. I actually don't know, but I think it's definitely, for example, I think if we increase the number of the days in the engagement data, if we, for example, we take 30 days and then we expand it to 60 days, we can see that the performance will go up once we scale up the data size.
Got it.
Actually, I don't quite understand the last question. Is the real items post a challenge for embedding? The real items, the fresh pins or very like if the pins.
Go ahead.
Yeah, I can understand. Like for example, the fresh pins or the pins without any edges in the graph. Yeah, I think that really makes sense. I think this definitely is some challenge that we have in the embedding, and we do have some like a customized way to predict the fresh pins. Yeah, so we have some unique ways, or maybe some additional ways to predict it just for the fresh pins.
What about for fresh users? Actually, is now another question. So if a user is just coming into Pinterest, how do you guys kind of like cater to a user who has no interactions yet? It's just fresh and just coming. How do you guys cater to that? to such a user? I mean, it's like the cold start problem in recommendation systems.
Yeah, I think we are, while we have the user embedding, but I think if you don't have any user engagement data for these users, we basically will treat it as our user cohort, and to generate this user embedding for the fresh for the fresh users. And then after you engage with pings, we'll quickly pick up we have some kind of real-time signals to quickly pick up your very recent engagement data to iterate your user embedding.
Makes sense. Awesome. Then one final question here from Nimish. It says, can you talk briefly about rollout strategy and the serving infrastructure?
Rollout strategy, serving infra. Yeah. I think, for example, when I can talk about, for example, when we create a new model, usually we will do some of the online experiments to measure the performance of this model. Or for example, if we train our new embedding, we will first experiment it in a small surface to update its candidate, and to try to measure the performance of this embedding to compare with the production model. And then if it works well, and then we will launch this new embedding in in this small surface, and then try to expand to other surface. I don't know whether this is the rollout strategy you mentioned. And the serving infra, yeah, we do have our ML platform team and ML serving team to help us to serve the model. We also have some in-house serving infra team to help us to do some online signal service, and or for example how to compute some online predictions faster. For example, how to fetch the features at one time for all the candidates. For example, in some of the use cases, we have hundreds of candidates to predict, and how to fetch these candidates at one time. That's also the serving infra team will take care of.
Got it. Awesome. Thank you so much. I think that's all the questions on the chat channel. Thank you so much. I really appreciate it. And thanks a lot to everybody for coming. Really appreciate your questions. It was really nice. Thanks, Sai.